So Dr. John Byrd, our speaker tonight, is an adjunct professor of geology at the University of Utah and the president of ByrdGEO. He has both a BA and a master's from UC Santa Barbara, and that established his foundation as a field-based geoscientist that he utilized during more than 30 years as working in the energy industry for Esso, Exxon, Anadarko, Hess. Early in his career, he also got a Ph.D. in geophysics at the University of Utah, which focused on the neotectonics of the Teton Fault. And so John has been studying the Teton Fault for a long time. As an explorationist, John has been part of and led international frontier exploration projects, studying the Wyoming overthrust, the Hannah Belt, deep water. Since establishing ByrdGEO in 2016, John has consulted for many different companies, but his main focus is working with students, teaching graduate level classes and seminars at the University of Utah. Also summer field camp in Southwest Montana for the South Dakota School of Mines and the University of Houston, leading field trips through the Utah and Wyoming thrust belt, Tetons, coast ranges of California. In addition to geology, he's led registration efforts for the League of Women Voters in Houston and is on the board of directors of Tool Bank USA and the Houston Tool Bank, a nonprofit for nonprofits that provide resources for community improvement, disaster relief, and education in the greater Houston area. Please join me in welcoming Dr. Byrd.
Thank you very much, Mike. So, in part, apologies, I should have given my first talk at the Geologists of Jackson Hole meeting about 30 years ago when I was actively doing my PhD research up here. And so I'm excited. I'm probably more nervous than I should be, but we'll fight through that. So there's going to be a little bit of the old stuff that we did just to kind of establish a ground game for this. But what I'm going to talk to you today about is I'm not in a position, or I'm not going to give you, oh, okay, here's all these wonderful revelations. What I'm kind of want to do is to say, hey, maybe we aren't looking at some of the right stuff. And I'm going to admit to myopia when I was doing my PhD, which is not what you're supposed to do, but ends up happening. And in the process of doing that, hopefully show some things that we need to think about, and maybe this group, as a very active and vibrant geology organization, can instigate some additional work. So we all basically know where we are. So this is a very short aspect of the regional and sub-regional geology for us. But on the left this is actually an old map, a compilation of the Utah, Wyoming, and Idaho geologic maps, in which I just led a field trip for my graduate students down in Utah, and explained to them how the geology clearly changes dramatically along state boundaries, this is a wonderful one. They couldn't really understand how that worked quite so much, and I said, well, not only about state boundaries, but also on 7.5-minute quadrangles as well. And then this is again an old slide of mine, but basically shows the crux of the Teton Range, which, as we all know, is cored by this Precambrian basement rock gneisses. And the age scale that we go up to, all the age geologic epochs are represented here. And the Tetons have been at the nexus of geologic interactions throughout their history. So since 2.6 billion years ago, where you've heard from Carol Frost about the oldest evidence for subduction zone, which is in the north end of the range. to the Pinedale glaciation with Joe Licciardi and Ken Pierce's work, and then of course the ongoing seismicity. The focus that we're, of the talk is the Teton Fault. This is actually pre-LiDAR. So this is the trace of the fault, which we actually walked out. So, and David Susong, who is kind of the lost contributor in all of this, did an awful lot of this early work in the summer of 1987. He did a lot of the early mapping through here. And of course, now you've had talks on the fault trace and with the LiDAR, so the ranging data, anybody in the world can pick out the fault trace. And yeah, that is another long story that I could go into, but I won't. Then coming into this, this is just a general compilation of the different geologic provinces. It's a 1988 publication from Brian Wernicke and Gary Exon and Zeke Snow. But we're right here at this corner point. And there's controversy, and we'll talk about this a little bit here as to whether or not this area, which is the Great Basin or the Basin and Range, actually extends up into the Tetons. A number of people, I know you've heard a number of nice talks from Ryan Thigpen, and Ryan and others say that this is we're at the eastern, this is the easternmost expression of the Basin and Range. I think that there's some room for discussion there. Then on the right, this is a compilation of quaternary or active faults. These are faults that have evidence of displacement in the last 2 million years or younger. And the historic faults, so here's up here in this corner, where this is Hebgen Lake. So this is the magnitude 7.5 earthquake in 1959. This other red area here over is the Lost River Fault from the Bora Peak earthquake. These are the two large ground rupturing earthquakes in our vicinity. And note that the Teton Fault here in yellow is latest quaternary. So and we'll talk briefly about a quick summary of the evidence for all the earthquakes we have on the Teton Fault in the last 15,000 years. Another same thing, but we're also going to be talking about some different formations. And this is just to kind of throw out some of these terms so that we don't get into this too much of a rat's nest of, well, wait, what the heck is he talking about? We're going to be focusing on, in terms of from these stratigraphic intervals, the Huckleberry Ridge Tuff, which is 2.01 million years. It was the largest eruption out of the Yellowstone caldera. And the Huckleberry Ridge Tuff, we see outcrops of that in the at the very northern end of the range, or excuse me, in the Teton Wilderness. We see them on the back side or the west side of the range, and as far south as down into Steamboat Mountain is the southernmost expression of the Huckleberry Ridge Tuff. Below that, there's a limited amount of exposures, but there's this rather curious lacustrine unit called the Shooting Iron Formation, which Dave Love originally described, and this is another unit that we look at with regard to some implications for when the Teton Fault moved. And then on down, we have the Conant Creek Tuff, the Kilgore Tuff, which is more or less the same age as this, a little bit younger, the Tewanot Formation, and the Coulter Formation. So these are Miocene units, so they're 23 million to 4 to 5 million years in age. The Coulter Formation is, you would imagine, up near Coulter Bay and over to the east of there. It is a very thick accumulation of Miocene volcanic rocks that have not been studied in detail since 1985. And that's one, to steal one of my closing comments, this is something that there's lots of opportunity out here. The Tewanot Formation is basically those white cliffs that you see behind the fish hatchery and all along Flat Creek there. It is a very curious unit. It represents, and we'll talk about the lake and Teton Lake and its implications for when the fault started to move and how much it's displaced. Everybody good with that? It's all old news. So this is an incomplete but rather extensive list of people that have done an awful lot of seminal work here in the Tetons. And apologies to those that I've left off of it. But you know, it goes all the way back to the Hayden survey, when the Hayden survey came back here in the 1870s. And then my graduate students, I assigned them a paper, but you know, with the description was 15_ black welder. And they thought, oh, wow, it's 2015. And then when they realized it was 1915, they kind of went, wait a second, why are we reading this old stuff? But as you all know, this is, you know, one of the most beautiful places in the world to live. And that is in large part due to the geology, I would argue. And so if you're going to be a geologist, what better place to come and work than to work in the Tetons and Jackson Hole? So, you know, the 1956, the Wyoming Geological Association used to run annual field conferences every year. And this 1956 conference was here in Jackson. And much of the fundamental work that Dave Love and others did is included in this. And going back and reviewing this before this talk, I discovered that, boy, I thought, you know, I've come up with some new ideas, and now Love had seen this. So, you know, there's very few things that are a new idea, right? Again, the whole slew of different studies here. This is a table that I compiled for my dissertation way back when, and then has a couple of new additions to it. But basically, one of the biggest problems that we have here in understanding the uplift history and the geometry of the Teton fault is that in the valley, we don't have any really older stratigraphy exposed. The glaciers have come in. You've heard all about the glaciers coming in the Pinedale and Bull Lake glaciers, and they've wiped everything out. And the other thing that happens is that normal faults, just by their nature, bury their evidence. And we'll talk about that in a bit. But you can, you know, just a quick perusal of the amount of throw. So that's the amount of vertical displacement on the fault, and you know, what it looks like, and the age of it goes all the way from 23 million years for the inception of it, up to it not starting to about 2 million years ago. So that's an awful long time. You know, you'd like to have a little bit more closure on that. And then the displacement ranges go from, you know, total displacement of on the order of 2 kilometers to as much as 13 kilometers, which is something that you've heard quite a bit about lately. So again, a broad range of offsets. I can tell you that, you know, as a exploration geologist in the energy industry, if I made a presentation to my management and said, oh, well, it's between 2 and 11 kilometers, they'd basically say, well, okay, yeah, there's the door. Come back later when you can tell me something meaningful. So, but this is part of the problem, is that there's this all these different ways that we can look at this problem. And as a result of that, we come up with this wide range of estimates. So what do we know? Well, we going from most recent to older times, we do know that there have been at least 5 post 15,000 year ground rupturing earthquakes on the Teton Fault. And you've heard from Darren Larson and the wonderful work that he's been doing at Jenny Lake, Christy Ross and Mark Zellman and Glenn Thackeray. We've got a pretty good handle on what that post 15,000 year history is. And we'll talk about that a little bit more. When we step back from the Pinedale at 15,000, the next marker that we have are the Bull Lake glacial deposits at 150,000 years. And we have hints, and I'll show you some of those hints, today of how much displacement has taken place related to that, but no really hard data. And part of that is because the Pinedale has come in and wiped out all the much of the evidence for the Bull Lake up along the mountain front. You know, glaciers. The youngest one takes credit for all the work the old ones did. And then going backwards from there, we have a number of different units that we can look at that give us some hints. Summer Brown and Ryan Thigpen have collected this new thermochronologic data, where with that data, it's a wonderful new tool that we can look at the thermal signature of the apatite and the helium entrained in the rocks, and that gives us an idea of when they pass through a certain temperature level. We know that the isotopes are released at that temperature level, and that gives us, then we can say, okay, from then on, this is what we're looking at. There are a lot of assumptions that come into that. And then the overall thing that we're fighting here is that, and this is Dave Love diagram from his block diagram from 1973. And you can see here that, so here's the Teton fault along the front of the range. And a normal fault, the mountain range comes up and the valley drops down. And so anything that used to be on top of the range or on this side is buried down here, and this is what we call the hanging wall. And anything that's been uplifted invariably gets eroded. So it makes for a tough job of correlating across these kinds of faults. And it's really what the best tool that for looking at this are drilling wells in there so that you know what's in the subsurface. And the other is using reflection seismic data, which is the main tool in the petroleum industry. There are actually some old reflection seismic lines that were shot in the valley back in the late 70s and very early 80s. I've seen them, and you can't see anything. So wow, I was really excited. I talked to some old friends at Exxon. They said, oh yeah, we'll send that to you. And I think they were kind of laughing as they put them in the box, because in those days it was all paper, and sent me like basically a cloud of nonsensical information. So let's take a quick look here at what we do, these are again a kind of a review of some of the time windows that we've looked at, and this is the approach that we took. I worked with Bob Smith and a number of other people. In trying to understand the 2 million year to present history of the fault. And the motivation for my PhD was the rebuilding and reconfigurement of Jackson Lake Dam. Because, in the late 70s, I forget the date now exactly, but of course the Teton Dam over on the other side of the range failed spectacularly. Luckily, before it was completely full. So it was a catastrophe, but what it did was it prompted the Bureau of Reclamation to say, okay, wait a second, we need to take a look at all of our dams across the country. And in the process of doing that, they came to the conclusion that Jackson Lake Dam was in fact the most seismically hazardous dam in the country. So in the mid 80s, they undertook a reconfiguration and reconstruction of the dam, and had done some seismic hazards work in that. And we came in while that was going on and did a whole series of different studies. So we looked at everything from 2 million years to present, and we used these different, and we also used large scale, I used large scale information to try and determine what the basin looked like. So what's underneath Jackson Hole? What's the geometry we're looking at there, using geophysical techniques? And then we looked at the Huckleberry Ridge Tuff. We looked at these, what I'm about to show you, are these Bull Lake surfaces, which we believe are tilted as a result of movement. And then we actually went out and mapped the fault. Dave Love's map from, the very nice compilation for the Grand Teton National Park, his map, the fault is actually in the wrong place. And Dave, but that was not his task. His task was to look at resources and find uranium and among other things. And he was not a quaternary geologist. And he got it in a number of places. He got it right, right above Spring Lake. He's got it in the right place there. But a number of other places, and he didn't. So we went out and did a detailed mapping of the fault, and we looked at the escarps. The escarps formed in the Pinedale moraines. And then our study was the first study to actually trench and date the fault. So we excavated a trench at Granite Canyon, and we found evidence. For my interpretation at the time was that we saw evidence for 2 earthquakes in that trench, one at about 8,000 years and one at 5,500 years. But no evidence for earthquakes since then. And again, the problem with when you're digging a trench is you can only go so deep, right? So remember that the normal faults is taking everything down, and so your backhole only has a certain amount of reach to it. So we were able to see those 2 events. Subsequently, we have 7 additional trenches that have been excavated along the front. So one with a really big backhoe at the ski resort, right there at Buffalo Bowl, and then a whole series of small hand-dug trenches at Lee Lake, Steamboat Mountain, and then right up here at Ski Lake, among others. And kudos to to Mark Zellman and Glenn Thackeray and Chris DuRoss for going out and digging these trenches by hand, because these boulders are big and it's not fun. So get through digging this thing. Now you've got to have the mental capacity to try and interpret what you see through there. And it's been wonderful. And then the lacustrine sedimentation work that Darren Larson's been doing has been very, very insightful. And then the other thing that we did was, I was getting a Ph.D. in geophysics, and so it was supposed to be an earthquake hazard study. The problem is that there are no earthquakes on the Teton Fault. So if you don't have any earthquakes to study, it's kind of hard to do that geophysical earthquake study. But what we did do was, during my time when I was at Santa Barbara, my master's advisor there, what he had was he had established a whole series of benchmarks out across the San Andreas. And what they did was, we went out and we measured and looked for the elevation changes in those benchmarks to see if we could see strain associated with that. So we thought, okay, let's do one of those, but like on steroids across the Teton Fault. And my thought was, okay, yeah, we'll go out and we'll build all these, put all these benchmarks in, and I won't have to worry about it because this is kind of a longer term thing, and we won't see any results. So the benchmarks, there were 44 of them, from all the way from the head of Cascade Canyon, down the mouth, down over Hidden Falls, out along the range front, down the past the old horse stables there at Jenny Lake, and all the way out to Dead Man's Bar. So it's 18 kilometers long, and there is a benchmark every 500 meters. And some of them are more visible than others, but if you haven't seen them, that's great, because we don't need people out there looking at them. So we were looking to try and get at the contemporary strain and a possible uplift across the fault. And we'll talk about those results briefly. So this is basically, I've taken all my work, and then of course all these wonderful studies that Chris DuRoss and Mark Zellman, Glenn Thackeray have done out here, and then also Darren Larson's work and others' work in Jenny Lake. And what we can see is that each one of these dashed and colored lines represents where the extent of them represent where we see evidence for these paleo earthquakes. So the youngest event, which is at 5,500 years ago, we see evidence for it all the way up here at Steamboat Mountain, and We see evidence of it in Lee Lake. We see it in Granite Canyon down Buffalo Bowl. And then by inference from some of the publications or publication associated with a field trip last year, it looks like it is probably here at Ski Lake, but the guys haven't published these results yet. So that's why it's a slightly different color and more dashed. But this 5,500 year event ruptured the entire mountain front. So the correlation of that and comparison of that with other historic earthquakes, this was a magnitude 7 or greater earthquake that caused this rupture. Then there are a series of earthquakes between 7 and 10 million years. So we see evidence for 4 additional earthquakes. We don't see them all the way along the front. We just see them in the central portion of the range front. And then below that, there are the magnitude, the 10,000-year-old fault rupture. We see that all the way down here at the south end at Buffalo Ball, and we see that up here at Steamboat Mountain. And then the older events, we don't really know, but we do see them, evidence for them at Jenny Lake. So one of the things that this says is that when these earthquakes rupture the surface, so, the inference is that some of them rupture the entire fault and some of them rupture only a part of it. And the big conundrum here is we haven't seen evidence for a ground rupturing earthquake on the Teton Fault in the last 5,500 years. So, that is a big question mark in terms of, is it dead? Or are we just not seeing the evidence for it? And you have to remember that what these are very large earthquakes that are rupturing the surface and giving us some indication that we can see them. You can have a whole series of magnitude 6 earthquakes, which will cause a lot of shaking, and they would not rupture all the way to the surface and give you that evidence. So we can't see that. So there's a big question there in terms of what these really represent. And then this is just this compilation that shows that for this 5,500 year event, we see displacements of 1.5 meters at Ski Lake, and then about 2 meters up here at Steamboat Mountain. So this is really nice compilation to show that earthquake ruptured the entire thing. So quite a bit of activity, none in the last 5,500 years, but between 5,500 years and 15,000 years, an awful lot of earthquakes. But then we lose our markers. So, or in part. So one of the things that we see is when the fault ruptures is it creates this escarpment at the surface. So when it comes all the way to the surface, it actually creates a step in the landscape. And back in the day, we walked out here with surveying rods and actually measured the slopes on these. Now with this new tool of LiDAR, this is from the north end of the fault, and everybody can see this lineation through here, I would guess. That is the Teton Fault. So it's very easy to see where it is. And in fact, the detail that you can get from these LiDAR data enables you to measure the surface displacement on this. And a lot of people have done this. This is just kind of a, oh, well, gosh, I did it too slide. But, that we had about 25 profiles all the way along the fault. And we saw this distribution where you had greater displacement in the central portion of the range and less displacement as you went to the ends. Subsequent to that, using the LiDAR data, there are a whole series of studies in here that basically corroborate that, but have more points where they're able to compare it. And there have been a number of things that come out of this in terms of trying to, if these scarps are registering a displacement in the moraines, which are as old as 23,000 years old, they tell us that there have been earthquakes that more earthquakes and more offsets, at least in the central portion of the range, basically in front of the Grand and up towards Mount Moran. Here's Moran Bay right here. So you see this kind of normal distribution, if you will, this curved shape of the distribution, the implication being the greater amount of displacement in the middle, and then it dies off to the edges. So then the next thing back from those Pinedale evidence, if we go back and look at the Bull Lake, here's Ken Pierce and Joe Licciardi's map showing the extent of the Bull Lake ice. And it went all the way down here to Munger Mountain, Red Top. And this ice was 150,000 years is when the deglaciation took place. And there was 3,000 feet of ice in the valley. So it went all the way over the top of the buttes. We're definitely cold right now if we were here 150,000 years ago with this really large extent of ice. And what happens is that then the next younger, the Pinedale ice, created the moraines that we see along the mountain front today at Jenny Lake and Taggart Lake, Phelps Lake, down to Granite Canyon is the southernmost one. But the ice sheet associated with the Pinedale didn't get really much further south of Jackson Lake. So all of these deposits out in front of there, therefore, are older glacial units. They're 150,000 years old. And one of the things that we see associated with that is we see some rather strange topography. The most notable one being Flat Creek, or excuse me, Fish Creek, which comes out of Phelps Lake, starts draining towards, here's the Snake River coming down through the southern portion of the valley. Fish Creek comes roaring out, and any self-respecting creek would want to go into the big river and get carried on further down. Gets to about 250 yards or, quarter mile, maybe a quarter mile away from the Snake. And then it says, no. I'm not going to join you here. I'm going to turn right and I'm going to flow all the way down along the west bank until I finally join up with the Snake River down here south, down to the south end. And the reason for that is that this whole area in here is topographically lower than the Snake River. And so the creek is feeling the topography and is flowing into this area of subsidence. We see the same feature over here just south of Jenny Lake. And again, another area of subsidence here. And in fact, if you're at the Snake River overlook over on the, and look across with your binoculars, you expect to see the mountain front coming up, but you're seeing the tops of trees because that whole area is several meters lower than where you are on the Snake River. And this is, again, when you want to say, oh, okay, yeah, boy, why aren't we smart seeing this? Well, no. Dave Love and John de la Montagne documented this back in 1956. This is a whole series of their profiles. They have about 12 of them. And they documented this subsidence. So using a handheld altimeter, for example, here on this I and C, and these are all along through here, you can see that they documented that the area over towards Wilson and along the west side of the valley is actually topographically lower than the Snake River. And thank goodness for the Army Corps of Engineers maintaining the levees, right? So we decided, well, that's wonderful, but what we're going to do is we're going to go and, well, this is too small, but we went out and we used a theodolite and got a much more detailed profiles of these. And yeah, sure enough, what do you know? Love and Montaigne, de la Montagne knew what they were doing, and we documented that, we corroborated their results. What we did then is, if you're going to do a Ph.D. in geophysics, you got to do something that begins with M, meaning a model, and make all kinds of different assumptions. So what we did was I created this model that says, okay, if I take the geometry of the fault and put a certain amount of displacement on it, can I match this profile that we see in the surface? And sure enough, give you enough time and effort, and actually it wasn't that hard. We can see that if the fault is zipping somewhere between 45 and 75 degrees, so that's the angle is going into the subsurface, you can create this topographic profile with about 125 meters of displacement on the fault. So that's 125 meters in the last 150,000 years. So that's good rapid movement. But you know, what if Joe Licciardi's on? Joe, we need to go out and map or age date some of these surfaces to make sure we know what the actual ages are of them. Stepping next back, we look at the shooting iron formation. This is a study that Leopold and Love did. And these circles here are the outcrops for the shooting iron formation. The black is the Teton formation. This is this lacustrine unit. And the upshot of their study was that looking at the palynology in the shooting iron formation, they said, well, you know, and it's all very fine-grained rocks, and so the Tetons were not there. So they said, okay, the movement on the fault postdates the 2 million year age of the shooting iron formation. The other thing that's very interesting about that is that there is an outcrop of shooting iron formation at 10,000 feet, and these are at 4,000 feet. So that's an awfully deep lake, if that's the case. In which we're going to talk about more. So this gives us an estimate of 2 million years, or you know, maybe at 1.7 million years or younger for initiation of the fault, is what their argument was. The next one back is we look at the Huckleberry Ridge Tuff, which is 2 million years old. It crops out on Signal Mountain. We can say, okay, Signal Mountain, the fault is inclined at 9 to 10 degrees. If we take that and project it over towards the Teton Fault, we get about 2.5 or 3 kilometers of displacement, or excuse me, yeah, three kilometers of displacement line. But this dashed line tells you we really don't know where it goes. So it's basically playing the projection game and taking this over here. We're going to revisit this. So this is something that basically David and I came up with. But when you're the guy providing the money, you get to be first on the list, right? And then we have a whole series of I did additional work on it. We look at the magnetism associated with the Huckleberry Ridge Tuff, and basically didn't come up with any super significant results other than saying that it had been tilted. Ken Pierce and Lisa Morgan, this is where my myopia comes in. So I'm worrying about the Huckleberry Ridge Tuff, and right below it is this unit called the Kilgore Tuff, which is about 4.5 million years old. But all I did was worry about the 2 million year old tuff. And the 4.5 million year old Kilgore Tuff is dipping, inclined into the sub at a steeper angle than the Huckleberry Ridge Tuff. And it actually is also inclined at about the same angle as the 10 million year old Teton formation. So Morgan and Pierce argued that actually it doesn't look like there was much displacement between 4.5 and 10 million years, and so that the Teton Fault started about 4.5 million years ago. Both the Huckleberry Ridge comes out of the present day called Yellowstone caldera. The Kilgore Tuff was erupted from the Heisey Volcanic Center, also part of the Yellowstone system, up in over near Heisey. So the argument was that because it was able to be deposited into the Flora-Jackson Hole, that the Tetons were not a significant barrier to that cloud of ash that was deposited in through here. So, okay, great. Now we're back at 4.5 million years. So I'm going to use an analogy for you here. I'm guessing that a number of you have been to Paris and been to the Louvre, or if not, that's fine. But when you walk into, and of course, everybody wants to go see the Mona Lisa, and you walk into the room where the display is, and there's this huge crowd of people, and trying to see this small little portrait, and that's all everybody's focused on, right? Well, it turns out that if you pay some attention, there are actually 3 additional masterpieces around you there, But I would argue that 95% of the people that go into that room never take a look at these because, one, they're tired of fighting to try and see the Mona Lisa. Why do I say this? Well, I think that one of the things that we're missing, and that's the gist of my talk in here 40 minutes in, is that the Gros Ventres are the equivalent of these other masterpieces. That everybody comes into the valley. I mean, when everybody's driving up, where are they looking? Well, they're looking towards Yellowstone. Thankfully, most of them keep going, right? But the ones that stay are looking at the range and in awe, as they should be. But very few. Everybody's got their backs to the Gros Ventres. You know, it's the poor stepchild of the geology, and there's a tremendous amount of beautiful, wonderful geology in through there. And so what I'm going to try and convince you is that maybe we aren't paying attention to the right thing in some ways. So one of the things here is to look at the status of the actual mapping and detailed analysis that's taken place here. So if I, this is from the state, statewide map. This is very large scale. Here I'm using my finger. The Gros Ventres are over here, and so the geology is documented. But when we go and look at the U.S. Geological Survey documentation of detailed mapping, you can see that this whole area has no detailed maps. So no maps at 1 to 2,000 scale. And in fact, up in the Teton wilderness, these are preliminary maps that Dave Love put together back in the 60s. So no recent mapping has been done over in the Gros Ventres at all. And to my knowledge, there's none planned right now. When you go to the Wyoming survey, here's the Jackson, they have Jackson Lake West and Jackson Lake East. And when you look at what they say about Jackson Lake East, they've been looking at the superficial deposits, but the bedrock mapping is unmapped. So we don't have any real recent work that's been done over in this area. And as a result, there's a lot of stuff floating around in the literature that hasn't been updated since the 1970s. When we look at the Gros Ventres, so here's Jackson Lake, here's Blacktail Butte is right here. Over here in the Gros Ventres, there are a series of structures. These black lines represent folds or anticlines that are coming out that we can see in the range. And this red line here is a thrust fault, so it's moving in the opposite sense of the Teton fault here. And we see that they are trending north-northwest or west-northwest. And I've taken the liberty of dashing this one called from Steamboat or Shadow Mountain, excuse me, called the Ramshorn anticline. And I've said, well, wait a second, what happens if it continues on out here underneath the valley floor? Oh, okay. I thought that was a question I was trying to hear. So back in the 60s and before, there are a number of oil and gas exploration wells drilled up here in the Gros Ventres. And there are actually active gas seeps up in the Gros Ventres. And so there was a lot of trying to find stuff wherever they could. And so some exploration work that was done here. And as a result of that, what we see are a number of cross sections associated with the Ramshorn and Spread Creek anticlines. So this is from Dave Love in 1951, and you can see that the state of understanding that point was that, okay, here I have a data point. This is what I see on the surface, and here's another data point from these wells. And then he did not really feel comfortable kind of filling in the blanks in between. But the main gist that they got out of this, and this fit in with the overall dogma, was that these Cretaceous age rocks, so 90, maybe 70 million years is the youngest of those rocks, were sitting on, they're basically vertical, going into the, and the pinion conglomerate was sitting right over the top of them. And we know that the pinion conglomerate is about 64 million years old. So because this is going right across the top of it, the interpretation is that these folds in the Gros Ventre formed prior to 64 million years ago. So that is what we refer to as the Laramide. It's a very confusing term. And this is from Dave Blackstone, who probably, is comparable to Dave Love in terms of the amount of work that he's done through his career here. And I've highlighted, he says that Spread Creek anticline, which is this one right here, and this is his later interpretation, 1989. So you can see in the 38 years between these two publications, there's a lot more chutzpah in terms of projecting what we see down in the subsurface. He says that it's expressed to the surface and they're unconformable by this Paleocene pinion conglomerate. So that means it has to be, as I just said, more than 64 million years old. So hence everybody says, okay, the Gros Ventres are more than 60 million years old. And it's basically just a static mountain range that sit there is landsliding and getting washed down into Jackson Hole. And it's not really, if you want to see active tectonics, why would you go and look at something that's 64 or million years old or older? Well, in 1956 in the guidebook, Dave Love led a bunch of people up through Ditch Creek. And this tan color here, or this darker brownish color here, is the Miocene Teton formation. So this is the lacustrine deposit. And then this gray color here are these Miocene volcanics of the Coulter formation. And he said that when you look at both of these formations, they're both dipping about 20 degrees to the west. So they're inclined at 20 degrees on top of the Jurassic Sundance Formation. So similar to relationship to what we saw in the previous cross section. So thus it appears that the western closure, so the western dip, is post-middle Miocene in time. So this is in 1956. So this predates the cross sections that we had previously, where when we look at the top of these anticlines, it says that they're 60 million years or 64 million years or older. But this says that they are actually, and they weren't sure of the Teton age at this time, so they thought it was Pliocene. But this says that this fold is being tilted younger than after 10 million years, 9 million years ago. And in fact, if you look, you see that there are Huckleberry Ridge tuff outcrops over here on Shadow Mountain as well. And they are also dipping. And the next slide, when this is a Google Earth representation of it, that we were just looking at this area here. There's Huckleberry Ridge tuff here. And you know what? There's Huckleberry Ridge tuff here, right down on that, adjacent to the river. And it's dipping at about 15 degrees there. And I floated to that and sampled it and looked at it. Anyway, so there is there's the Huckleberry Ridge tuff is here. Down to here is about 350 feet, or 1,300 feet, 350 meters in elevation change. So if we just look at this portion of the area and we draw a cross section through it, here's Shadow Mountain. This is a schematic, but I think my point here is that if we take from Shadow Mountain down to this exposure at the river, we see that there's 350 meters, or 1,100 feet, which corresponds to an overall dip of 4 degrees, inclination of 4 degrees over to the west. The measured structural dips are 12 to 18 degrees, so it's 3 to 4 or 3 to 5 times almost more than that. So this may be incorrect and conservative, but what it says is that Shadow Mountain has been tilted and uplifted in the last 2 million years. Much different than something being uplifted in the last, that was dead 65 million years ago or older. So that is a very significant, potentially significant aspect of things. But this has not been looked at in detail for quite a while. And so, my suggestion here, in fact, not my suggestion, I would say that we need to go out and take a look at this. I've gone out to look at some of these outcrops out on Shadow Mountain, and just made the mistake of doing this in the last 2 years, and the snow and the cold in my old age. I didn't spend a whole lot, and that and the bear that was running around up there. I just thought, okay, maybe she does want me to come home, so I won't go out here and do this. So very interesting with regard to these structures. Yeah, so when you take that observation, this is an oblique view. Here are the buttes. Here's Jackson. Here, we're sitting here. These blue-colored blobs here are the outcrops of the Teton Formation. And that you can see that the Teton Formation is distributed along the east side of the valley and the flank of the Gros Ventre. And in fact, there is Teton exposed all the way up at Signal Mountain as well. In this area, the Teton is at 6,400 feet. Up here, it's at 9,800 feet. So this is what Love used to estimate, in part, the thickness of it. But if you're deposited in a lake, you're basically the sediments are deposited horizontally. The rocks in this area are dipping at 45 degrees, 25 to 45 degrees. So they have been deformed and uplifted or tilted. If we go in and look at it, if we go in and look at the geologic maps, we also see that up here on top of Table Mountain, and this was another failed attempt. This one, he was a big brown bear, down in here. Actually, I was coming up through here, and an awful lot of deadfall. And anyway, I got about to there, and then I said, nah, that's it. But these are outcrops that need to be reevaluated because of the significance that they're sitting here at 98 or 9,600 feet. And then even higher, Love mapped the Shooting Iron Formation up here, which is 2 million years in age. So if these units were not deposited in this location, or if they were deposited in this location and they haven't moved, then it was a very deep lake. Or what's happened is that they've been uplifted into this position. Taking this, and so this is coming in and looking at it in greater detail. And then in Gros Ventre. But let's play a game here. So this is a shaded topographic map, and again, the blue is the distribution of the Teton. The black lines are the active quaternary fault scarps that were published by Chris DuRoss and Mark Zellman on their recent map of the Teton Fault. And what happens is, and I apologize, this was at 1:45 in the morning last night. I didn't finish this, but the idea is that now if we look at this distribution and we say, okay, well, here I've got outcrops of Teton in all these locations. Now, over in this area, this is all extensively glaciated. We don't see any evidence for it, but it doesn't mean it wasn't there when it was deposited. We don't see any evidence of the Teton along the front of the range. But again, that's also not surprising. These are kind of pumiceous, really fine-grained sediments that don't preserve well when you put a glacier over the top of them. So if this could be, this would be a conservative size for Lake Teton. If what I've done is I've said, okay, if the highest elevation of the Teton is up at around 9,800 feet, and so all these red contours on here represent areas that are above that elevation today. So if the lake was filled up to that point actually, we can't hold the lake in. The present day topography won't support the lake. There's not a catchment here. There's not a container here that will support the lake. So this is actually, I wasn't really comfortable drawing this, to tell you the truth, because it's a little, I have so little data. But this would be some idea of what possibly a maximum extent for the lake would be. And that means you'd have to have much higher elevation all through this area. Now, there's a smattering, well, more than a smattering, there's a wide distribution and array of data on the Teton. I've been chasing it for a couple of years now, and much of it just doesn't come easily. So I believe that we need to come out and take a new look at the Teton. I'm not convinced that it's up to 6,000 feet, which is what Love had for his maximum. But there's also an opportunity in there because there's a bunch of pumice layers in it that with the new dating techniques, we can see the sequence associated with it. There's also an interesting correlation, and I drew this here in part because Mike and I have talked about this a little bit, but there are Miocene volcanics down here at the south end of the valley, and there's Miocene intrusives that show up just below the pass and also on the buttes. There is an old master's thesis on it, looking at the geochemistry of them, but really nothing. We haven't done anything in terms of trying to understand what their significance is tectonically. And I stopped this here because one, there's a big old fault that runs through here, but it may have been that there may have been a volcanic edifice down at this end that could have blocked the lake from going out in this direction. And similarly, you could have had that up to the north. So let's take a little bit of the implications of what we have here. If the uplift of the Gros Ventre is actually 2 million years and younger, then it may be that we might see something in terms of the earthquakes. And so this is the large-scale distribution of earthquakes between 1955 and March of this year. And you can see there's a parabola. Here's Yellowstone. This black is the Hebgen Lake earthquake. Of course, we don't get it. We're in the seismic gap, hence the interest in what's going to happen on the Teton Fault. And then this continuation of seismicity down along through the what I call the Wasatch Teton corridor in here. Part of the motivation going way back in looking at this is that before the Bora Peak earthquake in 1983, the Lost River Fault zone over here looked much like what we see here. So it's like, oh, okay, are we going to fill in this gap? And we, as seismologists, we'd like to see a continuum. So when you see this break in here, it raises some questions. So let's take a look though more closely at the earthquakes right in the vicinity of right around the Tetons from the 1950s to the present. And I've basically this table on the left, I am anticipating questions from folks with regard to some of these. So the larger earthquakes, magnitude 4.5 earthquakes are in yellow, and the 4s are in purple. And you can see there's a significant zone of seismicity up the Gros Ventre Canyon. And there's also an interesting zone and activity over here around Alta, just in this area through here. I'm sorry, I can't tell you what the causative agent is for that, but I'm going to give you some suggestions for what we might be looking at here. This yellow line here is a cross-section that corresponds to an early study that Bob Smith and his Ph.D. student Diane Dozier, who left the strings for her plants hanging above my desk when I came in after her, did in this area. And so the same thing. And what they put out and did a series of portable seismometers in 1981 and 82, and they saw this cluster of earthquakes, and then they have this seismic line, very poor, quality image, but they saw that this zone of earthquakes here corresponded with an area that looked like it was a fault. That they were imaging a fault within the Gros Ventre, which lo and behold is not far away from where the Ramshorn anticline is. There was previous work that Bob and Jack Pilton did, and Dave Love was a co-author on this, looking at seismicity in the early 70s, and the conclusion of this was that, in fact, that the earthquakes activity back in the 1920s may have been a contributor to the Gros Ventre slide. That combined with an awful lot of rain at that time, and I think everybody's heard that story. So this is not the first time that people have thought about what earthquakes in the Gros Ventre mean. But right now there is, if I don't have them here. Anyway, the number of seismic stations in the Gros Ventre, 0. So there's not a whole lot of close monitoring going on in that area. The other thing, and this is conjectural at best. So here's the location of this level line that I referred to earlier, and the topographic profile of the level line. This big dip here is because it comes up off along the moraine and along the mountain front here at Jenny Lake, and then drops down and comes up not at Hidden Falls, but there's an old horse trail just past that we came up through there. When they had horse stables there at Jenny Lake, they were none too happy with me when I was out there with the drill drilling holes in the boulders because I spooked a horse. Anyway, I'm here to tell the story, so that's okay. But what we expect to see on this level line was we didn't expect to see a whole lot actually. But between when we first surveyed it in 1988 and then our next survey in 1989, we saw this very, very anomalous signal where the valley floor was coming up relative to the mountain range. But wait, the normal fault says the valley should go down and the mountains should go up. So exactly the opposite of what we thought. Now you say, oh, okay, well, wait a second, how much is this? Well, this is as much as 5 millimeters. So it's not like you're going to feel it moving under your feet, but the precision that we had on each one of these measurements, we had a precision to within 1/4 millimeter of the elevation on it. So very, very precise out through here. And so this ended up becoming yet another chapter in my dissertation. And this uplift happened to coincide with filling of Jackson Lake after they completed the dam. And we thought that maybe this was like putting your fist or your head under your pillow, and with the weight of the water coming in from filling Jackson Lake had propagated out through the valley, and we were seeing this bulge here. I mean, the story behind that, and nobody from the Bureau of Rec here, right? Okay. So they spent $80 million back in the mid-late 80s rebuilding and recompacting the dam. And so they did it on time, and everything was hunky-dory. And then in the winter of 1988, we had a good rain year, a good snow year, and in the spring they got record runoff. So the idea originally was to just kind of fill the lake slowly, but they had this huge runoff in the spring. And they went to open the doors of the dam, and they'd under-engineered the motors for opening the dam doors. So they couldn't open it and let the water out, right? So as a result, what happened was the lake rose 30 feet, basically almost instantly, okay? Yeah, it didn't fail, dam didn't fail, but what happened was you created this load here. Now, the benefit of 35 years later, I look at this signal and I look at what I just talked to you about, and I think, maybe the signal in here is associated with earthquakes and seismicity over in the Gros Ventre. Can I point to the individual earthquakes? No, I'm just here waving my hands. But I think that this is something that's not a bad way to look at it. And what we, with subsequent surveys, we saw that yes, there was still some uplift in the hanging wall, but and across the valley. But then, oh wait, things started to go down. Oh, then they came back up again, and then they dropped down again. So basically, to a certain extent, we're seeing the valley floor breathe on the order of millimeters. But you know, the reproducibility of these elevations in these benchmarks is actually quite amazing. And the last time we did this was 21 years ago. So time for another survey, right? And so that's you know, maybe there's a link here, because we couldn't convince people of the other story that we came up with. So are you guys okay? You know, I've been going for a little while. Okay, well, I'll roar through this. So on the northeast side of the range, there is we're going to step back from contemporary activity to the Hominy Peak Formation, which is a 50 million year old volcaniclastic unit. So it was erupted out of up at Hominy Peak, up on the northeast side or northwest side, excuse me, of the Tetons. And what is very interesting about it is that it comes in and it's sitting on top of these rocks down in here are Devonian in age. So they're in excess of 300 million years. And this Hominy Peak Formation, because volcaniclastics will come out and they will blanket things, but if you give them a canyon, those ignimbrites and that ash says, okay, great, I'm going to come in here and I'm going to dump everything I have here. So the Hominy Peak is filling a canyon that was on the order of 1,000 feet deep. And it is sitting, and this is something that occurs at the surface, right? This is not something that's in the subsurface. So we know that this portion of the range, and in fact, this is present not only up at Hominy Peak, but it's also at Grand Targhee. So if you go to Grand Targhee, there's Hominy Peak right there at the parking lot, and then a little bit further to the south. That tells us that that portion of the range was exposed at 50 million years ago. And in fact, the Hominy Peak is sitting on top of another conglomeratic unit that has eroded out some of the older rocks. So we know that in fact that those older rocks, you know, the range was up at 60 million years ago or 65 million years ago. So we see evidence for this uplift. Thought, well, okay, nobody's really been paying attention to this. This is great. You know, I can make a big splash. You know, I've had conversations with folks that have about the significance of this. Here's what do you know? You go and look around and you find Dave Love, 1978, did all this work. So so this is Dave's cross section, or actually a artistic rendition of it. The next one is not quite so artistic, but in this up near Hominy Peak, you can see that here's this 50 million year old unit sitting on top of this Pinion conglomerate, which is Tertiary Cretaceous in age, so it's on the order of 65 million years or thereabouts. And these two units are eroding down into these Paleozoic rocks all the way down into the Devonian. And this red is the feeder system for the Hominy Peak eruptive center. So, and what he was able to measure is that you can see that the Hominy Peak Formation is dipping 25 degrees to the west. But the underlying Devonian units are dipping 7 degrees to the west. Well, things get deposited horizontally. So if we rotate the Hominy Peak back to horizontal, all of a sudden now the western flank of the Tetons is actually dipping to the east. So things have flipped around in that regard. And Dave Love used this as evidence for what he called the Targhee uplift, which I actually don't believe was there, but that's a whole nother story. So this, I think that this is very, very important in terms of telling us what the early history of the range was, and when the range was at the surface. We know that these Paleozoic rocks were at the surface 50 million years ago. So we either have to bury them a lot and then bring them back up on the Teton Fault, or there's something fishy going on here that we have, that we have to rectify that with some of the thermochron data that's being collected. And believe me, the thermochron data is really exciting. It's a wonderful new way to look at it. I just think that we have to kind of start scratching our heads a little bit about the way we're interpreting it. So finally, he's done. So I think that basically, hopefully, I've demonstrated to you that there's some pretty good evidence for some recent uplift and tilting of the Gros Ventres, and that we really need to take a look at these, because if you go back to that cross section of the Huckleberry Ridge Tuff, going off over, dipping off over into the Teton Fault, and I published, oh yeah, there's three kilometers of displacement because of the way the Huckleberry Ridge Tuff goes in there. Well, actually, if the Huckleberry Ridge Tuff has been uplifted and tilted by movement in the Gros Ventres, that dip may have nothing to do with the Teton Fault, right? It may be something that is completely independent of it. So maybe the displacement is very limited on the Teton Fault, and what we're just seeing is the early phase of it. I don't necessarily think that. Tiwanaku, the same thing. We have this kind of conundrum in terms of the distribution age and the elevation of it, the structure of it. We need to go back and look at that. And I'll tell you, I've started doing some of that. And there's outcrops that Dave Love mapped up above the Gros Ventre slide to the north of there. And I'm glad that I was there by myself, because if somebody had been there with me, they would have wondered who I was talking to, because I was kind of quietly cursing Dave Love, because I was saying, Dave, there is no Tiwanaku out here. This is all glacial drift. What were you seeing, man? Come on. And I feel somewhat justified in doing that, because I'm old enough that when we excavate, that I have personal correspondence from Dave Love, which is some of my more cherished possessions. And when he had the trench open at Granite Canyon, he came out. I met him at the trailhead, and it was a rainy, wet, horizontal, wind blowing October morning, and I met him. And it was the first time I actually met him. And I said, Dr. Love, it's very nice to see you. Sorry about the weather. And his comment was, seen worse. Not a big deal. So we hiked on back into the trench. And he was just gobsmacked by he goes, I can't believe you guys found this. You're able to excavate this. He had no experience with trenching faults. And then he proceeded to ask a whole series of really good, tough questions. And he had been, he's recognized this early uplift over in the Gros Ventres. And so he was right on line there. And I should also say that Ken Pierce was the one that pointed out the trench location at Granite Creek, suggested that to us. And we chose it at that time, because it was the smallest scarp we could find along the fault, and also because it was accessible. The old Bear Paw Ranch is in through there. We had to do a environmental impact statement of the impact of having the backhoe in the backcountry, right? And when the backhoe left, I gave up the rolls of all the barbed wire that I'd picked up that was still back in there from the old Bear Paw Ranch. Anyway, enough of an aside. I think we need to take a look at and think about doing some more seismic earthquake studies in the Gros Ventres and trying to understand what the relationship of those are. And if we want to try and tie those earthquakes to the subsurface, maybe we should document what's on the surface a little bit more extensively, and that doesn't exist. But there is a big problem here, is why would the Gros Ventre be moving? There's not really a process or a driver that's really easy to put our hands on it. You know, there's probably on a larger plate scale motion sort of things, but the Gros Ventre are an enigma in many ways. The Teton Range, you know, I think that this 50 million year exposure needs to be considered in some of the uplift models. I alluded to the Miocene volcanics and the Coulter formation that we need to, that can give us some idea of what some of this 20 million year to, you know, 8 to 10 million year geology was in the area. And, you know, like my vita for you is, you know, I love, you know, I think that field mapping is essential. And I think that there's a lot of opportunity for us to do some additional field mapping up in the Gros Ventre and up in the Tetons. So I thank you for your attention. I apologize for going an hour and 20 minutes, but, you know, thank you very much. And hit me with questions.
If you could repeat the questions.
Yes, absolutely. Yeah.
Oh, do you have any speculation about the end of Pinedale, and, you know, we've got all these triggering events between 15,000 and 5,000 years ago, and then the quiescence as post-rebound? I mean, that's been thrown out.
So Anne's asking, you know, there is a publication which actually has gone into a textbook, so it has to be true, right? So there is by a woman, Victoria Hampel, yeah, and which with the pattern of earthquakes that we see is that we see an awful lot of earthquakes, evidence for them between 15,000 years ago and 5,500 years ago, and then nothing since. So the fault was moving much more frequently at that time, and what she did was she said, okay, well, if I take this ice and then I remove the ice, you know, the ice is a load on the crust. And I, you know, if I do that, then I relax things and boom, 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 all the earthquakes go. And because that load has been gone for, you know, 15,000 years, now that's why it's quiescent. So I'm not really comfortable with that. And here are the reasons. And one is I don't think that the ice load was large enough associated with the Pinedale. You know, and it was migrating. And it did not extend down into the southern portion of the range. So fine, if you trigger everything in the north and it goes to the south, you can say, okay, you're wrong. What was my second point? The other is that you have a direct analog with the draining of Lake Bonneville on the Wasatch. So, you know, we know that Lake Bonneville filled the entire Salt Lake Basin, and then when it overtopped its container at Red Rock Canyon, it dropped instantly 300 feet in over a period of 3 days is the estimate. So that would mean that we should see a whole series of earthquakes the same way right along the Wasatch Fault. We don't, but there's partly a reason for that. That is that we can't dig deep enough to get to 14,000-year-old earthquakes. So, and so it's like, okay, great. You're asking for a comparison of something we don't have the data for. I don't know that it's coincidental, but you know, it's curious. Yeah. I think it merits consideration. I think there are a number of things going on. Oh, there you go. I think, you know, it's an interesting idea, and that this please
You can't do that.
the nonlinear, you know, we like to see things be systematic, and you know, this is clearly not systematic, at least from our perspective. in our time frame.
Sorry, I'm just gonna make an intervention here. This is Cynthia Blankenship, President of GGH, and we had some technical difficulties in setting this presentation up, which meant we had to borrow a laptop from the library, which is now closed. So they're waiting for us to turn this laptop back in. So I'm going to apologize to the Zoom audience because we're running Zoom off of this borrowed computer, but we need to stop the presentation now for the Zoom audience. I'm very sorry. So that's that. We can continue the Q&A in the library if you would like.
You have other questions from the chat?
There were no chat
Okay,
questions
good.
as of a few minutes ago or a minute ago. So
Okay. All right. I guess Ryan's busy.
yeah. He'll get with you later.
Yeah, I'm sure. Sure. All right. So we can take this away. Any other questions with regard to things that I've thrown out there or just in general? Okay, well, great.
Yeah, so if there are no other questions, I want to thank John for a very thought-provoking presentation. And we have a small token of our appreciation. I want to remind everyone, November 7th, Dave Adams, and a field trip October 24th. So again, thank you very much. And if there's a question you didn't want to ask, John will be here for a minute while we wrap things up. Chairs on that side of the room go that way. Chairs on this side go this way. Thank you, John. Just want to return.
Oh, yeah.
My library card.
Oh.